Kelly Mahoney, and I'm a research meteorologist in NOAA's Physical Sciences Lab here in Boulder, Colorado. And I actually work on a team called the Hydrometeorology Modeling and Applications team. So we study a lot about floods. Floods are in the news all the time, so I think we kind of feel that they're important, but sometimes it can be really staggering to see the damage statistics, the loss of life that can kind of catch us by surprise. Floods are also really problematic for kind of secondary effects like water quality, and the way that our cities are built around, sewage and the management of water overall. So that's a lot of what we study here on our team in the physical sciences lab. We do have a very good body of research that's been developed over the last few decades that can identify trends in a lot of different parts of the country to say that floods are increasing or heavy rainfall is increasing. And that does tend to vary. It's a little bit more dramatic and easy to pick up in the Northeast and Mid-Atlantic and certain parts of the country, a little bit less obvious in the southwestern part of the United States. We're confident in a couple of reasons why floods are increasing, and that's because as the earth warms, the air can hold more water. And so you kind of end up with a bit of a stacked deck with, you can have the same kind of storm, but if you have more moisture to squeeze out of it, it tends to shift the likelihood of floods increasing. One of the most powerful tools that we have as physical scientists are computer models, and computer models are run for weather forecasting purposes, and they're also run for climate prediction purposes. And we try and improve them in some ways that are general between the two of them and then kind of specific to different needs. And so, computer weather models depend on the data that goes into them. So one area that we try and improve and understand the sensitivity of is what we put into it. So we try and take as many measurements as we can, and try and make those measurements as accurate as possible so that all of the data and numbers that you put into the model are going to give it its best start. But then once you feed it those data, you also need to have really good physics and equations and representation of physical processes in the model. And so there are a lot of ways that those can be improved. And so we try and analyze where the biggest errors come from in a computer model. And if we can pin it on either the incoming data or the physical processes, whether that's radiation, understanding what comes from the sun, whether that's cloud microphysics, all of the infinite interactions and things that are happening from droplet scale and up in clouds, trying to improve those by combining the measurements that we take and what we understand from equations, to get those more accurate. On the team that I work on at NOAA, the Hydrometeorology Modeling and Applications team, we also work on hydrology models, and that's again similarities, but focusing on the physical processes of when the water hits the ground. What do we know and not know about how that water is routed, what sinks in, what runs off, and how confident are you in those physical processes? And then again, if you only have a couple of measurements of stream flow along the way, what happens at those at locations in between those points, how far off from reality can models take you, how can you kind of constrain them? So we work a lot at that hydro and meteorology interface to understand where there is skill and where a lot of the errors may come up. In the face of projected increases in floods in the future, what can cities do? What can communities do? What can people do? And a lot of it hinges on being confident in the scientific predictions and projections. And so we as scientists want to do the best job that we can to give actionable information. A lot of what we often will say is, you hope for the best, but you plan for the worst. And so a lot of the work that we've done on in our group at the Physical Sciences Lab is to kind of ask those worst case scenario questions so that city planners and stakeholders can use that and say, if the worst thing happens, is our city prepared to deal with that? So there's a quote that also said, floods are acts of God, but flood losses are largely acts of man. And so getting back to that question then of what can people do if we know floods happen and we know floods are kind of more likely to happen in the future. Again, planning for the worst in terms of like community planning, floodplain management, insurance policies. Those are like high level strategic things that, again, we as NOAA and as scientists want to give the best data and the best guidance on. But then there's also increasing information about things that can be done at the local scale. And I think those are really exciting opportunities for every person to be able to have an impact, basically making their surroundings spongier, more absorbent for floodwaters. So floodplains, urban gardens, rooftop gardens, that kind of green engineering thinking is an exciting way that things can go from individual to citywide to upscale from there. Again, the creation and management of where does water go? How does it flow around cities? So creating and managing those floodplains and large areas that can retain and absorb water. Another big problem area of flooding relates to, sewage and water management. And so keeping the rainwater separate from everything else that we produce and end up using as humans is another area of planning and potential improvement. And then again, hoping for the best, but planning for the worst. And that comes from everything from the way you design your homes and communities to also thinking about how we actually warn people in real time about flooding. A number of different partners and stakeholders and interested parties work with us in the Physical Sciences Lab and with NOAA in general to better understand how the state of the science now can better serve their needs. And so it tends to be a really kind of excitingly diverse makeup of stakeholders that we are fortunate to work with. A lot of folks in the Western US in water management, so in the dam safety community, or on the West Coast especially, we work with the different water planners along the coast of California, trying to manage that tension between wildfire, drought, flood risk, dam safety and design. So everything from local governments to state governments and climate change studies done at the state level to national groups of the Bureau of Reclamation is a really strong partner that we share too. A lot of the work we do hopefully transcends those isolated projects that we end up working on and ends up feeding into the state of the science, kind of moving it forward.